For today's experiment, Vinay and I have chosen to demonstrate the consistency of torques among a balanced plank in equilibrium. I went to Home Depot and bought a cheap wood plank and a pivot point, but before we could begin my experiment, we had to organize what we were trying to solve. We wanted to do an experiment with balancing objects on both sides of the plank, and we decided to have one constant variable to stay at the same distance from the center of the plank for each trial, an attempt to balance the wood board by placing another object on the other side of the pivot. Therefore, we finalized on the idea to solve for the theoretical distance that would provide a torque equal to that of the constant in order to maintain equilibrium. We would have 3 trials with 4 different objects. In our pencil case, a water bottle partially filled, a metal lock, and a stapler. The objects would be balanced to the stapler as a constant. The stapler would be placed in the same radius away from the pivot for each object in one trial, varying its distance between the trials. This way, we could provide more data to better describe the distances between the constant and trial objects. In other words, the stapler would act as our controlled variable, the balance board our independent variable, and our 3 objects as the dependent variable.
To begin, we chose out our 3 objects, an art pencil case, a water bottle partially filled, a metal lock, and a stapler, and weighed each of them. We recorded their masses in grams since that was the only unit our scale could measure. Then, we placed the stapler on a set location on the board and used the other 3 objects individually to balance the board by testing out how far we needed to place them from the center of the board. We measured the distances and did this 2 more times in 2 separate trials by changing the distance that the stapler was placed. Eventually, we came up with these tables where the mass, distance, and torque experienced during the experiment were recorded. We also calculated the theoretical distance needed for each object to balance out the board in relation to the stapler, which is why the experimental and theoretical distance for the stapler is the same. We did this because the pivot that we had originally planned to use was ineffective, and we had to rely on a dumbbell. Its uneven sides and the carpet floor is why we believe that we will end up with a relatively high % error.
To calculate the theoretical distance and torque required to balance the board, we use the formulas net torque equals torque 1 plus torque 2, and torque equals RF, radius times force, and force of gravity equals mass times gravity. For the first object, we did the torque of the stapler minus the torque of the art pencil case, which equals to 0 since the board is in equilibrium and the total torque acting on the board is balanced out. We continued with 0.29988, the torque of the stapler, minus R times 1.1172, the force of gravity of the pencil case. We couldn't use our calculated distance because we knew that our experiment has many flaws, so in order to find the theoretical torque, we had to algebraically calculate the distance. Eventually, we came up with 0.268 meters or 26.8 centimeters. Then we found the theoretical torque by using the calculated distance. We repeated this for the 2 other objects in this trial, found the theoretical distances, and saw that the theoretical torque was the exact same for all of the objects. This is because in order to balance out the board, the torques must be equal on either side to balance each other out. Then we repeated these steps for trials 2 and 3 and found the same results.
We then created experimental distance versus experimental torque and theoretical distance versus theoretical torque graphs for each of the objects among the 3 trials in order to represent the idea that as the distance of an object from the pivot increases, the magnitude of its torque does so as well. As the graph slowly pan to the next one, you can see that the distance is represented in the x-axis while torque is on the y-axis. The slopes are all positive, indicating that as each object is placed further from the pivot, its torque also increases.
Our experiment generally produced a high amount of % error for the experimental and theoretical torques of each object. This is almost certainly caused by the uneven dumbbell acting as a pivot point, but also by the inconsistent carpet floor. At the time, no hard flat floor was available, and if I had time to do it again, I would have used my garage floor where it is flat and even. Another likely cause of this high % error could have simply been caused by my inconsistency in measuring the lengths of distances throughout my project. To make my project better, I would do multiple trials with this control at the same distance. in order to decrease the effects of wrong measurements. However, there were other limitations to how I could have performed the experiment. Since the pivot point was flat and wide, it consisted of a large range of how far I could have placed the board to maintain equilibrium, and when the board fell from its original position, I could not place it exactly where it was before. This affected the location of the center of gravity of the board and the distances I placed my objects. However, even with such a large percent error, we were still able to correctly represent the relationship between distance and torque, because both experimentally and theoretically, the magnitude of the torque for each object increased as the distance it was placed increased too. Overall, this project was a success.